Can you hear me?
Yeah.
May I start?
Yeah.
Okay. Hi, this is Team 2, and I'm the presenter, Yejin Hwang. So I'm going to introduce our project, which is domain generalization in human pose estimation via meta-learning. So let's start with a brief explanation about our background. Human pose estimation is computer vision task, which includes detecting, associating, and tracking semantic key points by localizing body joints from images or video sequences. And it can be utilized in various fields, such as medical rehabilitation or therapy, movies or animation, and sports motion analysis. The motivation for our project is that human pose estimation needs to be robust to variations such as changing clothes or occlusions or background. And also, we think that real-time inference will be very effective for further applications, so it needs some fast learning process with only small amount of data. Next, acquiring a data set with key point annotation for a new domain, especially in a large scale, is not an easy work. Therefore, the contribution with our project is in threefold. First, this is first approach to apply meta-learning methodology to human pose estimation task. And second, we design data set to be applicable for meta-training by using sampling and applying data augmentation methods from Coco dataset. And third, we propose novel labeled 2D multi-person pose datasets from 2 domains for meta test stage. Now let's move on to methodology part. Then what is meta learning? This is also known as learning to learn, and is the method for fast adaptation and generalization to a new domain. There are several common approaches for the meta-learning, and optimization-based approach is one of them to find optimal parameter with only small number of data examples. We chose Reptile as our meta-learner model, and this is first-order optimization-based meta-learning algorithm, which can optimize task-specific parameter an entire training dataset. And the algorithm basically works like this process. So when we say that the initial parameter starts from phi 0, as the meta training step proceeds, it goes to the direction of a vector difference between the phi 0 and the optimal parameter after training first task dataset. So it goes to phi 1, and then after training second task dataset, it goes to phi 2, and then likewise. So at the last, it goes to the phi n after training n task datasets. And then when the ungiven task is given, it can adapt relatively quickly. And we also designed task dataset for meta train stage. So first we split Coco dataset by over 60 categories, and the categories contains some objects such as like umbrella or tennis. And then after splitting dataset, we applied data augmentation on the splitted dataset. By adding rotation or giving noise on the image, and this was to improve model robustness on different domains. Next, we also designed 2 new datasets for meta test stage. So we collected yoga poster and thermal images from YouTube and Google, and these 2 datasets contains 100 images each. And then, as you can see in these 2 images, we've added 17 key points and bounding box for each of the image by using the annotation tool, and we've converted them to Coco annotation format. So this is how our dataset looks like. So it composes of meta-trained datasets and meta-test datasets. And for the learner part, we deploy top-down approach for human pose estimation, and the model generates heat maps from low-resolution features after the convolutional layers, and then it increases feature map resolution by upsampling using deconvolutional layers. Next, joint location is predicted on these generated heat maps. I'm going to share the results with our experiment. So comparing the pre-trained model and meta-learning model, these are the visualized outputs. So we can see that when we apply meta-learning, the joints are detected much more accurately compared to the ones from the pre-trained model. And shot number was set to be 32 in this experiment. And also, we can see that loss decreases in a much smaller number of epochs when we use meta-learning, and accuracy precision was 0.51 when we use COCO pre-trained, and it increases to be 0.546 when we applied meta-learning algorithm. These are the results from thermal data set, and it is similar to the ones in a prior experiment. So in this experiment, we can also see that the joint location became much more accurate by using meta-learning than when we use pre-trained model. And in this experiment, shot number was set to be 16. And comparing the accuracy precision, it increased slightly. It became slightly higher when we applied meta-learning. So in short, in conclusion, we found out that meta-learning truly enables faster domain adaptation. And second, a proper dataset design is very significant for meta-learning. And third, we think that our algorithm has a high potential to be applied to wider domains performing human pose estimation, since it converges quickly and it shows a more accurate results. So finally, for the future work, I think we can apply meta-learning to bottom-up model, not top-down model, for faster real-time inference. And we can also I think we should test the model generalization degree with more data sets from different domains. So this is the end of our presentation, and thank you for paying attention.
Okay, thanks. I have actually two questions. So in the conclusion, you mentioned that in the slide 16, the meta-learning enables faster domain adaptation. So is this the very first approach using the meta-learning in this problem?
Yeah, when we started the project, actually it was the first approach, but in the stage of the writing report, we've just discovered that the paper came in like this October. Actually, there is one paper with the meta-learning algorithm on human pose estimation, but at the time of the starting point of this project, it was the first approach.
I see. So then, did you have any chance to compare against that new paper?
This paper came out in October, you mean?
Yeah, I mean, yeah. Did you have any chance to compare against that?
No, we didn't have enough time to do that.
I see. I think that's worthwhile to actually conduct an experiment to compare against that baseline. And if your model has some advantage, at least on some points, then that should be a good contribution still. And we can still publish a paper based on this. So yeah,
Okay.
thanks.
We should complement that part. Thank you.
Any other question? Okay, thanks.
Thank you.